Welcome, everyone. It's my pleasure to introduce our speaker for today, Tilman Esslinger from ETH in Zurich. Before I say more about him, I wanted to remind everyone that you can pose questions to our speaker either through the Zoom Q&A or the YouTube chat, and we'll take a break or two during the talk to address them, so don't feel like you need to wait until the end to ask your questions. Please post them as we go. Anyway, back to Tilman. Tilman received his PhD in physics from the University of Munich in MPQ in 1995. And he's truly one of the pioneers in quantum many-body physics with cold atoms, having broken open the field with the first demonstration of a quantum phase transition between a superfluid and a mod insulator in a lattice of rubidium atoms. He's since branched out tremendously with exciting work on hybrid quantum matter made of cavity photons and ultra-cold atoms, and also demonstrating things like laser modulation as a very, very powerful tool to fundamentally alter the properties of atomic quantum matter, and much, much more. Today, he's going to tell us about driven and self-driven quantum many-body systems. And so with that, Tilman, please take it away.
Okay, thank you very much. And I would like to welcome everyone. I hope you all sit comfortably and I hope that moves further. Okay, and that you can enjoy, maybe you have a cup of coffee and maybe a muffin, depending on the time. And then I will tell you about quantum engineering of tunneling, and you will see what I mean with that. And it's about engineering quantized gauge field, so that the gauge field is no longer a classical field, but a quantum field. And then, as you may all know, that if you use kind of driven lattice systems, then you often have Floquet heating. But I will not tell you about Floquet heating, but I will tell you about how you can actually get rid of the Floquet heating. And then in the last part of the talk, I will speak about driven, systems where the dynamics is driven by dissipation. And that's a cavity experiment. The first will be a lattice experiment. So let me start maybe with a little bit of a view on lattices. So one way to divide lattice experiments is to divide them in experiments where you look at physics like mod insulators, quantum magnetism, and all the Hubbard type of physics. And there's also a big branch, and often that's done in systems where you actually have two-dimensional lattices, so kind of an array of tubes. And that is, there you look at driven systems, and you can create, for example, Harper-Hofstadter model, where you effectively have a magnetic field, or of course the Haldane model. And we are at the moment actually at a quite interesting time for lattice physics, because you have this nice question and challenge to combine both. Because we now fairly well understood many aspects of the Hubbard models, we also understand that in the non-interacting magnetic type of models, and to combine them two, that's a nice challenge. And one way to combine them is to create the following type of additional term in your Hamiltonian. And you see here one term of the Hamiltonian, and the main piece is this is your tunneling matrix element. It's a bit more complicated than usual. And both the amplitude, as well as in particular the phase, are operators. So you want to have a phase, a tunneling phase, which depends on what particles are on the different sides. So, well, you can look at it in this way. Imagine the blue particle is tunneling on top of the green particle. Then, depending on this configuration, it will acquire a certain phase, and this way the phase becomes a quantum field. It's determined by a quantum field, so it's a quantum field. And why would you want to do that? You would want to do that because in the longer term, you consider maybe looking at doing some quantum simulation of, for example, lattice gauge theories. And actually, there have been quite a few proposals discussing, could you create lattice gauge theories where you have kind of matter fields, typically you would think of fermions and gauge bosons, which create your gauge fields. And the work that I will demonstrate is one piece of that to create this matter gauge field interaction. And I think it's most related to a bit more longer proposal by Luca Barbiero and Fabian Grütz, who looked at a ladder model with similar ingredients as I will demonstrate. And there has also been a paper from the Munich group, from Monika Eidelsberger, a similar related work on such engineering of tunneling phases. Okay, so maybe let's start with the classical static gauge fields in lattices. And there, the idea is that you want to have a tunneling. If the particle, as indicated there, is tunneling once around the block, then it picks up a phase like as if there was a magnetic field. And now the change is, if you have the quantum gauge field, then you would compare those two situations. One particle tunnels around the block and no other particle is there, say that's a matter particle. And if there is a gauge particle, then it changes the flux. So that's the basic idea. Of course, you first need now to engineer the ingredients. And there, the question is, how can you engineer your tunneling? And there one can maybe have a bit broader perspective, tunnel engineering. And then I found this on tunnel engineering. So that's a picture of the Gotthard tunnel in Switzerland, the recently newly made Gotthard tunnel. And it actually was punctual, and it was punctual thanks, and that's actually was a advert or a press release from ETH, because they were also involved. And thanks to scientific calculations, costly delays were avoided. And similar approach we also always try, that we think and then try to avoid costly delays in our experiments. Okay, so but of course we will look at the engineering of tunneling first with the classical field. And typically what you do in the experiments, you have a lattice, and then you, for example, tilt the lattice, and then tunneling is suppressed, and you restore the tunneling by a Raman transition. So, and this tunneling element will then have a certain phase. However, you also have to make sure that in our model system of kind of one little plaquette, that the tunneling phase, say on between here and the next side, so the lower rung, is different than on the upper rung. and that it's not a phase that you can trivially gauge away. And usually this is done by having the driving laser field that is driving from here to there at a different phase than from here to there. And that's why you always have these additional funny beams from funny directions in those experiments, so that you have two different phases, or the relative phases have to be different. Okay, and now let's come to the situation that we are addressing. So we want to have a situation that you compare the tunneling if there is a particle or if there is no particle, and that's why it gets the head on this tunnel phase. And the starting point can be very similar. Instead of taking a tilted lattice, you could think of, okay, maybe I just use the atom-atom interaction, U, the collisional interaction on a side. And if there's then the tunneling is blocked, but you can restore it again with a Raman transition. And with the Raman transition, you might imprint a phase. Yet the problem is you have to break time reversal symmetry here. If you don't break time reversal symmetry, then you have you can gauge away your phase. And a key idea is here now to use two frequencies, a frequency omega and a frequency 2 omega, to imprint a phase and to be able to change this phase. And in a driving field, and I will come to that in more detail, you have a relative phase, and thereby you can now construct a tunneling matrix element where you can also construct the phase that you want to have in this tunneling process. And there had been along these lines how you can produce such Piles phases, density-dependent Piles phases. There had been proposals. There had also been work on creating complex tunneling and by breaking time reversal symmetry, so without density dependence. So there had been some work, and of course the list of work is not complete. So I list some of the work. Let's come to our experiment. We have a lattice setup which produces kind of a brick wall type hexagonal lattice. So you see our laser beam arrangements on the left-hand side, and on the right-hand side, you see the density or the intensity pattern of the light field. And we have a piezo. You see here this piezo, and that causes then the lattice to shake. In some of the experiments, we configure the lattice in such a way that we have dimers. And we do that such that we can, on these dimers, we can actually measure this tunneling phase. You see also there in the lower part that you have a driven, well, in the shaken field, it looks like a time-dependent force that you have in the system. Okay. So what are in the experiment, what are our observables? Our observables are a measurement of what's the fraction of double occupancies that we have in our system. And we can measure the magnetic correlations between neighboring sites. For example, we can measure whether we have singlets or triplets on those sites. These are the two main measurement observables. Okay, now comes the engineering of the tunneling matrix element. So we have these dimers with a little bit of an offset, which is a bit smaller than the U. this is necessary to avoid to have too many states. So this way we can then later create, or we effectively have a two-level system, which is easy again to analyze. And initially the particle, say the blue particle and the red particle, they form a singlet on this dimer. And then we drive the system by shaking, so that's simply shaking the piezo with two frequencies, with a frequency omega and with a frequency 2 omega. And with these we can induce a hopping of this particle onto the other side. So you can also, you can look at it that effectively this shaking causes a periodic modulation of this offset. And here you can also look at it in terms of maybe more like an optical transition. This ground state would be the singlet state, and the excited state is a doubly occupied state. And both of these, so we either can drive directly to this transition, but we have also a second pathway, which is a two-photon process. And now you can already see, okay, these two processes, they have the same starting point and the same ending point, and the relative phase might play a role, and maybe you can even interfere away. So you can think of it almost like an interferometer. And it allows you indeed now to engineer this tunnel matrix element and the phase of this tunneling matrix element. And the breaking of the time reversal symmetry comes in due to the relative phase between your two drives. So you have your frequency omega and frequency 2 omega, and there is a well-defined relative phase, which you can easily adjust. So what does that mean now for the total tunneling matrix element? The tunneling matrix element you can now write as a part which depends on both tunneling amplitudes, a term alpha, and a term beta with a phase and with a relative phase. And this relative phase is just at your radio frequency drive where you drive your piezo, you can adjust that. And the others you can also adjust by adjusting their amplitude. And now you can see that there are two possible regimes. Alpha may be larger than beta or vice versa. So if alpha, for example, here is smaller than beta, then you can enclose a zero. So you can, you simply add up your tunneling matrix elements and you get a resulting tunneling matrix element. And you get, depending on, in the experiment, the driving amplitudes, or in another picture, depending on your alpha and your beta, you get here a whole winding phase or a vortex for the phase in your parameter space, which you can determine in the experiment. So the next question is then, how can you measure this phase? And there the trick, because it is not so easy. I mean, one way would be, okay, you have one particle which hits another particle and another that doesn't hit a particle. But that needs increasingly complex systems. But we would like to know what is actually happening on our dimer. And the way our protocol works is the following. We adiabatically ramp up the driving field, and this is what is called H2 effective. So we have both driving fields with a certain set of parameters. And so it's like we bring it in a superposition between the ground state or singlet state and the doublon state. Okay, so it's in a superposition. And then we quench the system to by a radio frequency to the other spin state, to another spin state, so that effectively the particles are not interacting anymore. And then the evolution is the evolution of the non-resonant case. And that way we can compare the two phases. Kind of, we have a certain phase evolution upwards, and then does it match the phase evolution downwards? That gives a Ramsey type interference. So this is the data, what we do. Here is a timeline. First is this kind of adiabatic ramping up until half of those detected that they kind of the atoms that we detect in the singlet and the doublon are the same. And then we apply this radio frequency pulse and let the system evolve in this new Hamiltonian, and then we can determine when do we have a pi half, when do we actually have a pi half pulse. And then for this pi half pulse, we can now change in each measurement the timing of our radio frequency pulse. In terms of a Ramsey experiment, you would say it's like changing the time delay between the pulses. And then we get these detection fringes, and from these detection fringes we can determine this pulse phase of our matrix element. And one can look at it in terms of, well, that we split first into this superposition state, and then with a certain phase, we our second Ramsey pulse has a certain phase, and then we play the whole phase through and get and then can determine what our pulse phase is. And this is a round of results. So we change the relative driving phase, and then we measure always the pulse phase, and you see that this region corresponds to a situation where alpha is larger than beta whilst we change this driving phase, and that would be a scan somewhere around here. And we see that we have a phase jump if we are in this other regime, where alpha is smaller than beta. And well, there on the left-hand side, that is calculation. We can also see that obviously if we can adjust the phase between our two components which build up our matrix element, then we can also bring it to 0. And here is now the plot of the absolute value of this matrix element. And remember, this matrix element depends on whether on the configuration of the atom. So that gives you kind of the link variables for your tunneling process. One could, of course, wonder what is the route towards quantum simulation of lattice gauge theories. One could say, okay, the coupling mechanism between density-dependent Piles phases, so you have a coupling mechanism between matter and gauge particle that is working. And I should also, and I was a bit quick on that slide earlier on, there is work by Cheng-Chin who did kind of in a mean field setting, he did very nice pioneering work there. And this other paper that I put here. That is the Munich paper. The next step is, I think, would be to create larger systems. So in principle, there is no reason why one cannot couple the different dimers. There is no, from experimental point of view, there is no reason why not to couple them. It works the same way, but the question is then, what do I expect? What is my measurement quantity? And here in this paper, Luca and colleagues, they devised, for example, a ladder scheme which is fairly realistic. You have that you can engineer kind of minimal forms of gauge theories. So this is basically, yes, you extend the system. And you could also, of course, consider not just looking at lattice gauge theories, but to see what is happening if you have this additional type of interaction in your Hamiltonian, which personally I find just as interesting. And then, okay, you need to fulfill, there are some different levels of difficulties to build a real quantum simulator where the high energy physicists will take us seriously. I don't want to speculate too much on it, because I think in the end it's important just to do further steps and realize them, and then one will see how well they work. One should also say that, of course, there are not only neutral atoms around. So there are ion traps, for example. Also, there are proposals and work. And Rydberg atoms, they are also actually very similar. Antoine Brouet had in his Rydberg atoms, he had also recently worked on a very similar coupling scheme. You see, this looks very much like such a two-pass coupling scheme. And there has been a long review article recently on the archive. So I think there is an option now to have a brief to see whether there are questions. Otherwise, I move on with Floquet engineering.
Yeah, we do have a couple of questions. So Bill Phillips asks, what is it that makes the introduction of another particle give you a quantum rather than a classical field? Is it that this particle can itself tunnel?
Yes, that it can be itself in a superposition. Yes. Yes, very good. Yeah.
And then, so John Simon, one of our other panelists, asks, as you've said, to realize synthetic background gauge fields for charge neutral particles, some type of periodic modulation seems necessary to ensure that the field cannot be gauged away. Is the requirement indeed the same for dynamical gauge fields? One might think that since the gauge field can change in time, it could be non-trivial without explicit time reversal symmetry breaking.
No, I don't know. One has to be a bit careful kind of which particle can tunnel where, and so not all are supposed to be free. They may be just on a rung, and that's actually this has been kind of the simplest possible, I guess, simplest possible. Even simpler would be nice. Possible model that has exactly been worked out in this paper by Luca and colleagues.
Okay, and then one more question from Bill Phillips. Is the measurement of the Pearls phase, in the measurement of the Pearls phase, it appears that every point hits the theoretical curve, or is it a fitted curve within its error bars? How is this possible?
That we can calculate it. These are theoretical. I mean, they are, for example, these are theoretical curves. And let's see which other. Well, these are fitted curves. And let's see. Okay, I think that was where the data was. There is, of course, there are where experimental limitations come in is the preparation of the initial state. So kind of how many double occupancy or how many siglets do we start with? Hi, Bill. Bill, yeah.
Okay, we'll maybe do one more question and then we'll move on and save the rest of the questions for the end. So Mahede Hassan asks, it seems like you're just simulating a lot of isolated dimers. Is the lattice playing a role here?
In the experiment that I've shown, no. It's basically showing that you can a way how you can create this coupling and demonstrating the phase that you can create. The phase, I mean, you can also create, for example, not just sign changes, but 120-degree phases or something like that, which might lead, if you have more than 2 particle species, might be fun.
Okay, thanks a lot. I think you can keep on going and we'll save the rest for the end of the talk.
Thanks for the questions. Okay, so now let's move on. Okay, Floquet engineering. We all happy that we can do that, and in principle we can create almost all Hamiltonian, I guess. Well, there are always more Hamiltonians than we think. However, if you also look at the papers, I mean, there are lots of papers about heating and losses, and probably more even, increasingly more. And so these heating and losses, I was, of course, wondering who is responsible for that. And then I looked around and Googled Floquet, and I found the culprit, so Charles Floquet. And then I looked a bit, and well, he has done a lot. Even he was minister, the interior minister in France, so that's usually always a culprit if things go wrong. But actually, that is of course not true. This is not the Floquet, but the Floquet was Gaston Floquet, and but he was a contemporary of this probably more famous Charles Floquet. But after asking who is responsible, the other question is, of course, more helpful is what is responsible for, why does it heat? And there was a little bit of a mystery for a time that in our experiments, it seemed we had less heating. We could do some things that other people, for whatever reason, couldn't do. I mean, we for example, we could measure magnetic correlations. We could increase magnetic correlations in a system driven where we drive with a frequency near to U. And we could see that by increasing the hopping, we could increasing our exchange. So that was a bit strange, but we checked carefully. So the results were okay. But then we again thought, okay, why could that be? And there I think we quite well understood what the reason is. It's the lattice geometry. Most people work with cubic lattices, and we have this hexagonal lattice. And now you can look at what causes this Floquet losses and Floquet heating. It is that you drive your system, basically you drive transition. Maybe you want this frequency, that's your desired coupling. And however, you may also drive this 2-photon process to a higher band, and then you might lose your particle just goes in the higher band and then maybe even further up. And then what you see in the experiment is that if you scan your frequencies and then you plot the number of particles as relative to what you would have after 1 second. After 1 second for a static case, you see, whoops, they disappear fairly quickly. And then you go to this intermediate dimerized type of lattice. So that's between the hexagonal and the cubic. Then you see, well, I plot now both. The green is intermediate, and the red case is the hexagonal case. That's where what the lattice which we use to enhance the magnetic correlations. There you see we have a much longer lifetime and a much broader frequency spectrum. But when you look at now at the band structure along that direction, then you also see, these upper bands are flat, fairly flat, which is not so surprising because here this piece is missing. But that, of course, if there's less dispersion in the higher bands and in the lower band, you just have much more space to drive your system. So that was some insight that we had there. And then we did some in this paper, we did some work, we did quantum simulation, kind of comparing the non-driven with the driven system under identical parameters. But I want to go to another situation, another way how you can avoid losses and coupling to higher bands in a driven lesson, in a more general configuration. So, and this is now an amplitude modulated lattice, and you for example, you shake your lattice and you change your modulation frequency and take a spectrum of your atom number. I mean, quite a few people have done similar things. And then basically what you do then you can try to assign the spectra to what is happening. And for example, this 12 kilohertz peak, you can assign to a 2-photon transition to the P band. And this next broader peak, that is the single, that's twice the frequency. So that's a single photon transition up there. Okay, and then you can also see, okay, why is it so broad? It's just broad because it's a single photon transition and it has a much larger matrix element. So it's basically power broadened. So that's why it's so broad. So if you reduce the power, and here you see there's a 1/10 of the power now, then you get also a small peak. And for Bill Phillips, these are calculated curves. The full lines they are from a little simulation. The dots are, of course, our data. And now, well, now you can think, maybe you could now compensate these two processes so that you have one 2-photon process, that's the bad process. So that's maybe what you want your system to drive at. And then you add a very weak photon with the opposite sign, with the opposite coupling. So a bit like in a dark state or in coherent control, or I mean, like in interference, if you have two paths, you can interfere it away. And that's what we had looked at, both without and with interactions. And we also looked a bit in the literature. There is some work which is related. So other people were also thinking about interferences. That's maybe not so surprising. But I think in the Hubbard model and also with interaction, this type of approach had not been done, and it is actually very powerful. So what we do here, what you see in this graph, is we change the relative phase between our two driving frequencies. And one has to say here, this matrix element is just has a negative sign. That's why at 0 phase, you have the largest number of particles which are still in the ground band. So we look at how many particles are still in the ground band. And then you can also look at how does it actually behave as a function of amplitude. So that was with as a function of phase. You see if the phase is wrong, you lose all your particles. And if the phase gets right, you have almost we have very low losses. I will be quantitative on that in a second. And you can also change your amplitude, the relative amplitudes, for different main amplitudes, and you always see a peak. If you have the right amplitude, there is some peak and where the scheme works best. And now you can wonder, okay, you have a two-frequency drive, and what happens with interactions? So let's say you have a certain U. And here we compare now the static case, and that's the total number of atoms, and in the lower graph, it's the number of atoms in the ground, remaining in the ground band. So here, that's the total number of atoms, and then you have a one frequency drive, and there after a fairly short period of time, so that's logarithmic, so here's a second, so here's 100 microseconds or shorter, you lose your particles. In particular, you lose them in the ground band very rapidly. Whilst with the two frequency, it's almost like the static case. So this gave us optimism that that scheme actually works. And here are the time scales taken out of such curves as a function of Hubbard U. And you see that the scheme works, or kind of always works, and within a band of U of say -2 to 2, it actually works well. And then we got bolder. We thought, okay, let's look at what happens to double occupancy and even what happens to spin correlations under this driving. And there you see very clearly that the double occupancy go back to the single frequency case. And with the spin correlations, there is an increase of almost three orders of magnitude in lifetime. So the spin correlations, they 200 milliseconds, that's fine, they can work. So these measurement or this technique, this rather general technique that you look at your matrix elements and try to come up with a second path, and often fairly simple because you just take the second frequency with the right phase, that allows you to be very optimistic about the Floquet-driven systems again. So in that sense, if one wants to combine, I think there is a lot of room to combine, and one can be very positive about that. Maybe if there are further questions, I'm happy to take some more questions. If there are, otherwise I'll move on.
Yeah, we have a few more questions. John Simon asks, is the lifetime in the dimerized lattice longer in units of the tunneling rate within the miniband?
Is the lifetime longer? Oof, it's in the evening here now. Can you repeat the question? I cannot. I might be not able to answer.
Is the lifetime longer? Oh, there's here, John. Maybe you can elaborate on exactly what you mean.
So you made this point that the lifetime is longer when you do the modulation in a lattice that has this mini band structure. And I meant
Yes,
you reduce your tunneling rate when you do that. So I was just wondering if it's longer in units of that reduced tunneling rate.
Okay, I'll come back to that. I might now give the wrong thing, but it's yes, we are optimistic. I mean, I think all things where we thought it goes wrong so far, yeah. Okay.
Okay, so Mehdi Hassan asks, thank you for the nice explanation on the heating mechanism. To suppress the loss, instead of using different lattice geometry or the second sort of shaking frequency, why not just increase the lattice depth to flatten the bands?
But then often you don't have tunneling at all. And yes, so I think it's also with the lattice geometry, it just means for some things you need a certain lattice geometry, but maybe for some things you might have two options and one with flatter bands, then that's obviously the better one. Yeah. So yeah.
Okay,
it is
and then
tedious to get to all these processes, but actually it's worthwhile. Yeah, that's my conclusion from the recent work. Yeah.
And then Bill Phillips asks, I would have thought that between the 1 photon transition and the 2 photon transition, one of them should be forbidden, or at least somewhat forbidden. Why not?
There are forbidden bands which we don't couple to. So that was the first part, indeed, to figure out to which bands we do couple. And there we have 2 paths. Yeah.
Okay, great. Thanks a lot. Maybe we can move on to the last part of your talk and save the rest for the end.
Okay, so I guess, yeah, time is running. Okay, I will move on. So it's about driven dissipative interacting quantum many-body systems. This sounds awful. And the focus, I mean, awful, it's wonderful system, but it's a lot of, yeah, might be very complicated. But I will focus on one thing, and that's dissipative systems. And dissipative, where the dissipation is a crucial, it's kind of a key component. It's not just something which may shift a little bit a phase boundary or makes it just a little bit worse, the system, but in the evolution, the dissipation is the driving force. So without the dissipation, we wouldn't have, as I will show you, this chiral motion between different states. Okay, so maybe in very short, one could say you have a system, or in very general terms, you have a system which has a density mode that gets soft and a spin mode that gets soft. And here, what is plotted here along the horizontal axis is the difference between these 2 soft modes. So you have 2 soft modes and they have a certain difference, frequency difference. And if it's getting very close, if they're almost degenerate, these soft modes, then you see then dissipation kicks in most. If we have a lot of dissipation and the vertical axis is a measure of how strong dissipation is, then you have a rather broad region of a dynamical instability. So that's rather, and this is the dynamical instability is driven by the dissipation. That's what I will come to. But the system we look at is Bose-Einstein condensate in a cavity. And I would also like to point out that similar systems and are used, and I now at the very moment I see that I didn't put John Simon's name on there. I should, of course, because there is wonderful work. Yeah. Sorry, John. It will immediately get into this transparency. But I would also like to point out that all these people have something in common. I think it's almost all, yes, that it's bosons, and only Jean-Philippe Ponture recently put a fermionic lithium gas, strongly interacting into a cavity, and has there very nice results. Okay, so let me remind you of what these two modes are, and I will simply explain the simple one, that is a density mode. So what we have is this, well, I usually think of a superfluid refractive index inside the cavity. And then you shine light from the side, and at some point the system decides it's energetically favorable to scatter light into the cavity. And why does that make sense? It is a competition between 0-point motion and potential energy. So the Bose-Einstein constant, of course, if to lower the 0-point motion, you have a huge wave function and no wiggles. However, if the system comes up with wiggles, which cost kinetic energy, but then the system is able to scatter light into the cavity and then reduce its potential energy. So it's between those two, this phase transition. And it breaks C2 symmetry. Okay, so one can imagine that you have this structure forming when you shine light from the side, and it breaks the C2 symmetry. And now you can, of course, move on and think, okay, how can I play with this system further? And I mentioned a lot of people playing with such systems. And one thought that we had, okay, maybe let's take a spinor condensate and put that into the system, and then to also use the polarization of the pump beam so that you can play between scalar and vectorial light coupling. So one can imagine that then one gets additional coupling, and other things are happening. And the main thing that is happening is, well, you can again, you can again get a density mode, just the same as, sorry, here was a delay in my computer is too slow, huh? You can get again a density mode with a spin up, so it's a 2-spin condensate. You get a density mode just in the same way as before, but now you can also have something else. You can have a spin mode. And the spin mode is possible even though these particles, which are scattering and should kind of do Bragg scattering into the cavity, they have, they couple to the light with a different phase. And that way, they can constructively interfere and lead to a light mode. So the basic thing here is you can have those two modes, a spin mode and a density mode. Both can break a C2 symmetry. And they couple to different quadratures of the light field. Okay, and you can measure that. And as a function of, I mean, your control parameter, that is your polarization, okay? So you can have, well, depending here on the left-hand side, one polarization, and then you increase, and then it jumps to the other phase. Okay, but then, of course, we were interested in what is happening exactly here between those two phases, obviously. And then we saw things like that. So the left is a bit less than 60 degrees, and the other is a bit over this or in this critical region. Here is a typical self-organization data. You see this cavity photon number and you measure the phase. So it's a heterodyne measurement. And once you self-organize, you get a fixed phase. what we saw in the other case was a little bit jumpy photo number, but a nice running phase. The phase was nice to determine and running. And that's, so there's some dynamics in the system, and it's something you cannot just ignore and think, ah. So, and Nishan Dokra and Manuele Landini, well, they were leading these efforts. They figured that out. I mean, we also measured, I mean, here, I mean, it's time is running only briefly. So this running phase, of course, you can associate a frequency with it, and you can get sidebands to your output. So this is a kind of a spectrogram of what is coming out of the system. But very briefly now, what is behind that? Why is the system behaving like that? And basically what we have a Bose-Einstein condensate coupled by one quadrature of the light field, say, to the density mode, and by the other quadrature to the spin mode. Okay, so if you ignore dissipation, that would be your picture, and they would not talk to each other. Yet, if you now add dissipation, then the two quadratures get coupled by dissipation. And this induces the motion in the system. And you can look at it in a way that you have here the order parameter for the spin mode and the density mode. And you can look at it that if you form, if the density mode is formed, it's put into, it couples to the spin mode, and it does this chiral motion. So the running phase means that the system is evolving from one mode to the other. So since it's one of the last slides now, to have a picture, a pictorial, sometimes pictorial is nice. So the time axis goes, for example, from front to the back. And so what the system would do have a density mode, then a spin mode, density mode, spin mode of the other symmetry, and so forth. It's like in a Mexican hat, but now with two deeper regions, and then it's hopping in a circle. And you can eliminate the cavity field, and the minimal model to capture the basic physics is that you have your two soft modes, and then your dissipative coupling. You get one damped mode and one mode with a gain in the system, and this mode causes a driving. There are other damping mechanisms in the BC, otherwise it would explode. And these different spectrograms, they depend on whether your two soft modes have exactly the same frequency or whether they have different frequencies. And we could also measure, kind of, one can, based on this model that I explained you, one can calculate the phase diagram. That's a calculated phase diagram, the colors, and we can measure where is our region of instability, and this is determined by these measurement points. And the nice thing, one can also come up with a mechanical model for it, because these equations describe a position dependent friction force. This friction force, usually friction force are not position but velocity dependent. But imagine you have a hydrodynamic medium in a cylinder, and you have kind of, it's a rotating shaft in the cylinder. So you have hydrodynamic medium, and then you rotate it. So that's kind of the drive. And the position dependent means that you move away from the center position. And now you will see the friction force on the two sides of this disk will be different because it's a hydrodynamic incompressible medium, and that will cause a perpendicular force. And that is kind of the mechanical analogy. And then this mechanical system would spiral out. Our system keeps rotating, but the basics is the same. It keeps rotating that even, and we can get limit cycles in very shallow lattices. We get very stable rotational cycles. And in deeper lattice, they get broader in frequency. With this, I would conclude. I looked at these topics which are illustrated here, but I would like to take my time to thank the team. I first talked about our experiment in quantum gases in optical lattices, and the leading postdoc on this team is Konrad Fiban. And I also talked about the BEC in cavity experiment, and there the leading postdoc is Francesco Ferri, and the experiment is also Tobias Donner is working on that. We have two other experiments. That is a two cavity impact experiment where Toby and me are both PIs, and we have the lithium transport experiments, and where I have not talked this time about it. And I would like to thank you all for your attention.
Thanks, Tilman, for a really excellent talk. So we have a few questions for the end. So Didi Liebfried asks, is it too naive to say that the dissipation creates a line width for the coupling, which then increases the range of difference frequencies that make the modes couple?
Well, I don't know. I have to think about it. I mean, these similar behavior kind of is, of course, we get these non-Hermitian Hamiltonians, and you get these exceptional points here, these points. So whether that picture is enough, to me, not obviously, but I have to think. I mean, it's not that for me personally, I still would like to get a better and more intuitive understanding what is happening there. I mean, I'm pretty sure one can get a better picture, but it seems to be not so well. Not well. Afterwards, it will sound easy, probably. Yeah. I mean, the equations are there, so it should be there. Nothing completely surprising or so.
Okay, and we have a few questions from the panel. So Monica Schleyer-Smith asks, for your measurements of the spin and density modes in the cavity, the measurement